Hi everyone, so in this video we're going to be learning about improper integrals. Basically the idea with these is the same as the idea with normal integrals. We're just trying to find area, but there's going to be some kind of infinite number involved. And instead of plugging in infinity into the equation, we're going to look at it as a limit since, well, infinity always causes problems. So here's what it's going to look like if we graphed it out. Say we had a function, it could be anything, a function that looks like this. Say instead of finding the area from point A to point B, we don't just want the area over this segment, we want the whole area. Or maybe from here to the very end of here. So maybe this is approaching 0. We want this whole thing forever until x equals infinity. So maybe from 1 to infinity. And this ends up being pretty easy actually. We're either going to find out that the area equals infinity, or that means that the area diverges. Or we're going to find out that maybe this approaches 0 really fast, and we can actually add up the area, and it actually equals some number. Oops. So how about we do an example? So let's say we want to take the area of 1 over x minus 2 to the 2 over 3. Let's do 3 over 2. Let's say we want to take the area from 3 to infinity. And we want to see whether this adds up to some number, or maybe it equals positive or negative infinity. So is it convergent or divergent? So we're just going to go about this normally. We're going to take the improper integral. The indefinite integral. So maybe you can see that this is a u substitution. We're going to say that u equals x minus 2, and the derivative of x minus 2 is just 1 dx. So what's in here will end up turning into 1 over u to the 1 over u to the 3 over 2, which is the same thing as u to the negative 3 over 2. And I'll just write that as a side note. It'll turn into u to the negative 3 over 2 when we do the substitution. We're going to integrate this first and then substitute in x instead of the u. So we're just going to add 1 to the power. So that's 2 over 2. So it's going to end up being u to the negative 1 over 2, and we're going to divide by this new power. So we're going to divide by negative 1 over 2, which is the same thing as multiplying by negative 2. And now we're going to substitute the x back in, which is going to be negative 2. And over here we said u equals x minus 2 to the negative 1 over 2. And I'm going to rewrite this here neater. Negative 2 over, remember that 1 over 2 just means square root, and negative just means that it's in the denominator. So x, well, negative in the numerator means that you have to switch to the denominator. So x minus 2, there we go. And remember that we're evaluating this at x equals 3, and then x approaches infinity. I'm just going to write approaches here to make it a little bit more simple. So again, just like normal integration, we're going to plug these numbers in, see what happens. So negative 2, we're going to have a really big number, minus 2. So it's still going to be a really big number. I'm just going to leave that blank for now, and then we're going to minus this with the 3 substituted in, so that's going to be positive. Negative, negative is positive. 2 over the square root of 3 minus 2, which is the square root of 1, which is just going to be 2. So remember that over here we have the infinity. We don't really have the infinity. We have a really big number. X approaches infinity. So any number divided by a huge number is going to approach 0. So what we're left with from our integration is just 0 plus 2 over square root of 1. 2. So it turns out that the area from here, of this function from 3 to infinity, actually does converge to just the number 2. That's all we did. We took the area just like any normal integral, and we found out that in this case it does equal 2. It's convergent, at least from 3 to infinity. So let's do another example. Let's say we have, let's do this one, 2 to infinity, e to the negative 5p dp. What's this going to equal? Again, we're just going to integrate like we normally do. If you remember how to integrate e, let's see. Let's just do a quick refresher. It's e to the 2x. If you take the derivative of that, it's going to equal 2e to the 2x, right? And if you take the derivative one more time, 4e to the 2x. So we're just multiplying by this number in front of here. So don't get confused by the p. We're just replacing x with p in this problem. Instead of multiplying it, we're just going to do the exact opposite. So we're going to end up dividing this by negative 5 to get the integral. So we're going to end up with e, still e to the negative 5p. This doesn't change, remember. No matter if you're integrating it or deriving it, it's still the same. And divided by negative 5, let's put 5 in the denominator, same as negative 1 over 5. And remember that we're evaluating this from 2 to, well, a number that approaches infinity, a really big number. So we're just going to plug these numbers in just like normal. We're going to get negative e to a negative of a really big number. I'm just going to leave that blank, over 5 plus e to the negative 10 over 5 again. So let's just make this a little bit easier to see. Remember, when we have anything to the negative power, we can just put it in the denominator. Well, if it's in the numerator, we can put in the denominator with a positive power. So this is the same thing as saying negative 1 over 5 e to a really big number plus 1 over 5e to the 10. And remember, what happens when we divide by a huge number? It's going to end up being a really small number. So it turns out the area under this graph from 2 to infinity is actually going to end up being 1 over 5e to the 10.